Of all the moons in the solar system, ours is truly unique. It is the only one large enough and close enough to stabilize its mother planet, Earth. But our moon is spinning away at an increasing rate. Eventually, it will be too far away to stabilize the Earth. Take away the moon, and the Earth's tilt is altered dramatically, causing catastrophes worldwide. Extreme temperatures vaporize water and melt ice. Oceans could rise tens of meters. And massive dust storms and hurricanes rage for generations. Without our moon's protection, life as we know it will perish from the Earth. If the moon travels just 10% further from where it resides today, 40,000 kilometers or so, we'll reach a point of no return. That's when the Earth's rotation becomes chaotic, unpredictable, and unable to support nearly all forms of life. Scientists know the moon is retreating because they have monitored its movement for the past 40 years.
Neil, yes, we are getting a TV picture.
In 1969, Apollo astronauts leave the first of 3 suitcase-sized boxes embedded with reflectors. NASA's visionary idea is that one day we'll be able to use lasers to measure the moon's distance with more precision. They were right. And this is the tool they use today. The Apache Point Observatory, lunar laser ranging operation near White Sands, New Mexico. It uses those reflectors to calculate the moon's distance down to the width of a human fingernail. But measuring how fast and far the moon is receding is difficult. First, the laser pinpoints a moving target from a moving source, 400,000 kilometers away, through distortion caused by Earth's atmosphere.
We have a laser mounted on the telescope. The laser light travels out to the moon, where it encounters retroreflectors left behind by the Apollo astronauts. So it's a special kind of mirror which reflects the light directly back where it came from. Those reflectors send the light straight back to our telescope, and it comes back to our detector. We can measure the timing of the light traveling to the moon and back with extreme accuracy, and that allows us to measure the distance to an accuracy sometimes as little as 1 millimeter.
The advantage of a laser beam is that it travels long distances very quickly. The round-trip distance to the moon is 800,000 kilometers, so it takes light about 2.7 seconds to make the trip. But the Apache Point laser has its risks.
This is going to be our interlock control system. If any of certain safety conditions are not met, it will close a shutter so that the laser can't shine.
Aircraft are the biggest concern, so scientists alert air traffic control to keep planes out of the airspace.
It would not permanently damage anyone's eyesight. It would probably affect a pilot's night vision, which would be undesirable, so we try to avoid that.
On this night, the moon is mostly dark during its crescent phase. Using a guide camera to help aim the laser, Dr. McMillan locates a visible feature on the moon whose distance from the reflector is already known. From there, she'll know exactly where the reflectors are hidden in the darkness.
This is a crater called Pierce. It's way over here on the corner of the moon here, over here on the illuminated side of the moon. and then we'll go to Apollo 15 reflector, which is in the dark portion of the moon.
Tonight's sky looks clear to the naked eye, but the upper atmosphere is blurring the instrument.
Right now, it's not looking very good. It causes the laser beam to expand. It expands it, fuzzes it out on the way up towards the moon as it passes through Earth's atmosphere, and also on the way back down, coming back from the moon to our detector. So we get hit twice by that kind of shaky behavior from Earth's atmosphere.
With the laser aligned, it's now or never.
Okay, cross fingers. Okay, coming out.
The Apache Point lunar laser beam reaches the moon in less than 2 seconds.
If you were standing on the moon, you would see a bright pinpoint light. It would be pure green light.
This laser light is saturated with photons to ensure it bounces back.
The laser is strong enough that even though only about 1 in a quadrillion of the photons that we send out comes back and gets detected, because we're sending out many quadrillion photons, we're detecting a pretty fair number.
It's a bit like throwing a pile of sand at a mini trampoline 400,000 kilometers away and hoping a few grains bounce back. The more grains you throw, the better your chances.
Here's the outgoing signal being detected by our internal detectors. We would like the incoming signal to appear here. And there it is. It's a beautiful big spike. It looks perfect.
The decades of continuous measurements have shown that the moon is moving away from the Earth at a rate of about 3.8 centimeters per year. That might seem like a tiny distance, but over time it adds up.
Sometimes we take for granted how important this moon is to our pure existence here on this planet. Well, you've got gravitational pull from the moon onto the Earth, and so the moon is very tightly coupled to what's going on the Earth.
Our moon has the largest mass in the solar system in relation to its mother planet, and size matters. The large mass helps stabilize Earth. Gravity is the key to their relationship. It's the force that draws objects together. In space, it works a bit like balls rolling toward each other on a blanket. Gravity's strength depends on the size and distance of those objects. So the closer and larger the mass of the objects, the greater the attraction. And since the moon is the largest, closest body to Earth, the gravity between them is powerful. From 400,000 kilometers away, the moon's gravity holds our planet steady on its axis.
And this is very important because we have a very stable axis at about 23.5 degrees. Earth rotates around its axis once per day.
That smooth, even 23.5 degrees enables sunlight to spread widely across the planet, maintaining the Earth within a relatively narrow range of temperatures, a range proven ideal for life.
We have a very nice, very stable climate system here based on the tilt of our axis staying the same. And so this is very key because we need to have this stable situation for life to be able to take hold and then evolve and survive and thrive and be in the situation we're in now.
That stable axis also creates our regular seasons as it orbits the sun. When the North Pole tilts toward the sun, that angle creates a temperate summer in the northern hemisphere and winter in the southern hemisphere. And when the North Pole is tilted away, the opposite is also true. It creates winter in the northern hemisphere and summer in the southern. It's the moon's stabilization of Earth that maintains the sun rising in the east and setting in the west.
And if we had the Earth not in this nice stable axis thanks to our moon, you would see sunrises and sunsets happening at different times in different places in the year.
Without the moon's gravity, regular and predictable seasons would not have occurred, and plants and animals would not have evolved. Take the moon away today, flowers wouldn't bloom, and bees would no longer pollinate in spring. Geese would no longer fly south for the winter or north in the summer to breed. and seeds would no longer drop from trees in autumn to germinate. Even with the moon's stability, the Earth still has a small periodic wobble of 1.5 degrees on its axis. This is the natural result of gravity exerted on Earth by other, larger passing planets. As the moon continues moving away, the Earth will be thrown further off its axis, causing an even greater wobble. And larger wobbles can have big consequences for humans. Roughly 100,000 years ago, just a minor wobble changed the angle of the sun's rays on Earth, enough to turn lush forests into the Sahara Desert. An event that likely forced some of the first humans to migrate north out of Africa. Further north, from Europe to North America, the wobble prompted an ice age lasting thousands of years.
So even events such as the ice ages and things that we think of as major events on the Earth, think about how much more dramatic those would be if we didn't have this moon here.
The Earth would become unrecognizable. Climates would become unpredictable. Temperatures would vacillate wildly. So the moon's impact on Earth is critical. Its gravity even affects our tides. Astronomer Tom Murphy explains.
We have this polar view, the North Pole here, here's North America.
These blue particles represent the Earth's daily ocean tides.
The moon is off to the right, far off the screen.
The particles bulge directly toward and away from the moon.
If you're sitting in North America, you experience a low tide, and then a high tide, and then a low tide again, 12 hours later after the first low tide, and then a high tide.
Tidal cycles occur twice a day, each time the Earth passes one of two bulges. The tide that bulges toward the moon is a direct result of the moon's gravity pulling on the surface of the ocean as the Earth revolves past it. The tide that bulges away from the moon on the far side of the Earth is a result of water lagging behind. Since that water is furthest from the moon, the attraction is weaker. So the far side water is left slightly behind as the Earth rotates forward, producing the bulge and a second high tide. But it's not only water that experiences high and low tides. Entire continents are also affected by the moon's pull.
The solid Earth itself does deform under the lunar gravity influence, and it bulges as well. Now, it's only about a foot of amplitude from high tide to low tide, but the whole continent is rising and falling. It's not something that we can perceive. Sensitive instruments can pick this up.
During an eclipse, when the sun and moon's forces are combined, tides are highest at that time. But as the moon retreats, there will be no more eclipses. Without the moon's gravity, the 4-meter ocean bulge at the equator would dissipate and move towards each pole. As that water redistributes, in New York City, sea levels would probably rise. As well as in Brazil's Rio de Janeiro. Flooding would render both cities uninhabitable, leaving millions displaced, or worse. These disaster scenarios aren't science fiction. The moon is moving away from Earth. And when the moon's gravity no longer protects our planet, we're doomed. Laser light measurements, accurate to the width of a human fingernail, prove that the moon is retreating from Earth further each year. Just 40,000 kilometers more, and it's the end of life as we know it. To understand where the moon might be headed, we have to understand where it's been and how it formed in the first place.
The Earth and the Moon did not always exist. There was a time when they both formed. The way that the Moon formed was a cataclysmic event that happened on the order of 4.5 billion years ago. So this material is swirling around in the solar system, forming this protoplanet that's going to become our Earth. So your planet is molten, a lot of it's melted, this rock. And what happened was a very large Mars-sized body, so a very big piece of rock, came and impacted this early Earth.
It hit at an ideal 45-degree angle. A more direct hit may have destroyed early Earth altogether. A more glancing blow would have expelled less debris, the foundation for our moon today. Still, a collision between these two early planets seems to have been inevitable.
And these two planets were running almost the same orbit around the Sun. This configuration was an accident just waiting to take place, because running this close orbits, they're bound to collide at some point. And the Mars-sized planet banged into the early Earth. The rocky materials were ejected, a big cloud of rocks and debris.
And then that material gets ejected out far enough away from the Earth to go in orbit around the Earth.
While a lot of rocky material was blown into space, the heavier metals, like iron, sank down into the Earth.
And the metal parts melted together and formed the core of Earth. Well, here is a piece of iron that fell from the sky, and that is a spare part from when Earth was first formed 4.5 billion years ago. And it is an iron meteorite, and originally it formed the core of some small planet that has now been destroyed.
But not all of the rocky material fell back onto the Earth.
And so as that material goes around, it starts to hit together and starts to collide. And sometimes when it collides, it accretes together and it sticks. We call that accretion, where pieces of rock and dust and ice are coming together and sticking together. You eventually build up the moon. And so the moon was actually born out of this very early baby Earth.
Its birth took just 1 month. Not only is the moon the child of the Earth, it's also Earth's protector. Those pieces of iron and heavy metal that were left behind by what became the moon merged with the iron already in the Earth to give the Earth a larger molten metal core. Earth's metal core generates a strong magnetic field, which extends thousands of kilometers out into space. This protective field keeps Earth's atmosphere in place. Without it, cosmic rays from the sun would eliminate Earth's atmosphere and liquid water. So without the moon, there would be no air to breathe or water to drink.
If it weren't for the moon, if this planet did not have a moon, then we probably would not be here to talk about it. It's quite possible that there would not be life on our planet Earth if we didn't have a moon.
Earth might look a bit like Mars, lifeless. Mars is barren of both a thick atmosphere and liquid water on its surface. Early in its life, Mars probably had both, but its magnetic field soon faded, and any water either evaporated or froze solid. Scientists are still uncertain why, but one fact is clear. Mars never had a large stabilizing moon to help it reach its full planetary potential.
You could easily imagine you could have microbial life on Earth without the moon. It is possible life established itself on Mars or Venus very early on, but never really got control over the planet. But on Earth, what's another interesting thing is that life has kind of taken control of Earth environment and preserved life as an oasis for life. So it might be that without the moon, maybe life had established itself, but due to environmental problems, life would kind of have never gotten to take control, and Earth could have maybe gone an evolution the same as Venus. Venus has almost 500 degrees centigrade on the surface today and no life, and Earth might have fallen into a similar situation.
Our moon also protects us from meteors and asteroids. Some craters on the moon are 1,600 kilometers across, the result of collisions with massive space rocks, 270 kilometers in size. Without the moon, chances are that some of these asteroids will hit the Earth. And when they do, the consequences for life on Earth will be dire. The 11-kilometer-wide meteor that wipes out the dinosaurs is about 3 billion times more powerful than both nuclear bombs dropped on Japan. First, it vaporizes dust and blasts rock into space. Then, molten debris rains down across the globe. It starts raging fires across the continents, setting in motion a chain reaction of more heat and more fire. For an hour after impact, Earth's atmosphere boils to 260 degrees Celsius, hot enough to cook the dinosaurs alive. For 6 more months, smoke and ash prevent most sunlight from reaching Earth. The asteroids' combined effects kill nearly 75% of all species on Earth. Today, the Earth's human population is around 6.7 billion and growing. If a 1-kilometer-wide asteroid, just 15% of the size of the one that killed the dinosaurs, strikes the Earth, it could kill as many as 1 billion people. Even an ocean strike could trigger a tsunami that kills millions. So, are we destined to a future of unpredictable destruction without the moon's protective gravity as a shield? The answer may be buried deep in Earth's past. The moon's gravity has propped up Earth's stable axis for 4.5 billion years. Without it, life as we know it would not exist. But recent precise lunar measurements indicate our moon is retreating from Earth. Determining what this might mean for Earth's future requires searching for clues in its past.
We're up here in Big Cottonwood Canyon, and probably thousands of people drive by here on the way to the ski resorts every year, not really realizing what a fantastic story about ancient history of tides, the Earth, and the moon is captured in these rocks that are almost 1 billion years old. Well, these are very fine-grained rocks, and these fine-grained rocks are the type of thing that even normal geologists like myself would kind of drive by. But one day, somebody brought me a cobble from the creek, Big Cottonwood Creek.
Dr. Chan immediately realized these rocks are like few others in the world.
And we came up here, we started looking at some of these deposits and realized that really tell us an important story.
Before these rocks formed the Utah Mountains, they started life on an ocean beach. They're composed of ancient sand and mud. Over time, they hardened, preserving the sedimentary remains of the ocean's tidal rhythms.
These are some of the oldest known tidal rhythms. And this is in a regime where we used to be sort of close to a shoreline, and the ocean would come up along the shoreline and move some of the sand and mud. And so some of the sand and mud gets preserved in these different lines in the rock. And the way these lines or these rhythms alternate back and forth is telling us something about how the tides operated almost 1 billion years ago.
Dr. Chan concentrates on the alternating pattern of lighter, thicker lines against darker, thinner ones.
And some that are light-colored are telling us about times when the tides were strong and when the Earth and the Moon and the Sun were all aligned together. Those were some of the times when there was the greatest gravitational attraction, so those strong tides could move more sand.
Tides are strongest when the Sun aligns with the Moon. That's when gravity of both masses simultaneously pulls at the ocean's surface as they pass overhead. Twice a month, stronger tides, or spring tides, leave behind thicker, lighter layers. When the Moon moves out of the Sun's alignment, it causes weaker tides, or neap tides, twice a month. Neap tides allow finer, darker silt particles to settle, leaving thin, dark layers. To Dr. Chan, those alternating monthly layers are like tree rings, records of time laid down by the ancient environment. And that record tells her that time was flying back then.
Looking at how many rhythms there are and seeing that there are perhaps more rhythms, more numerous, and that's maybe telling us that the Earth was spinning faster. So when they're faster, the days are shorter, and there's more days in the year.
4.5 billion years ago, Earth spins almost 4 times faster than today. Days are only about 6 hours, and Earth's axis is nearly straight at 10 degrees. But over the next 4 billion years, the Moon changes all that.
Early on, the Moon was closer to the Earth, and so you have a greater gravitational effect on the tides compared to what you have now. And so the size of those tides is changing throughout time, being larger when the Earth and the Moon are closer together because that distance between them is smaller.
When the Moon forms at around 32,000 kilometers from Earth, it's over 12 times closer than today. Earth's oceans appear shortly after, and the Moon pushes tides 4 times faster than those today. The liquid stretches across what little volcanic land exists, and the tide's friction against the Earth's rotation begins to slow our planet down.
Over time, you have the tidal friction. The tides just moving back and forth across the surface of the Earth creates friction, and that also contributes to the slowing of the rotation of the Earth.
Over the next 3 billion years, the continents form and tidal friction slows Earth to about 18 hours per day. 500 million years later, days last 22 hours. Adding a fraction of a second every century adds up to our current 24-hour day. In 1 billion years, the Moon's gravity on the tides could slow Earth's rotation down to 30-hour days. But gravitational pull between the Earth and Moon goes both ways. And because Earth's mass is larger, it exerts more pull on the Moon. The Earth has already slowed the Moon's axial rotation to only once a month.
Looking at the Moon, we always see the same face of the Moon facing towards the Earth. And the reason is because we are in a synchronous lock, Earth and the Moon. And so gravitationally, the Moon is sort of stuck with its same face looking at the Earth all the time. And this is because the Earth-Moon system is so gravitationally tightly bound that we're coupled together.
Earth's gravity has another, more profound effect on the Moon. When the Earth rotates, friction from its ocean beds drags the daily lunar tidal bulge slightly eastward out of a direct Earth-Moon line. That bulge of water has so much mass that its gravity pulls the Moon forward in its orbit, causing the Moon to retreat further and further away from Earth.
When you take a rock in a string, the faster you throw it, the further it goes out. And same with the Moon, the faster it goes, the further it goes away. So the Moon is receding away from Earth.
Based on geologic records over the last billion years from the pre-Cambrian period, not only is the Moon retreating, it's picking up speed.
And back in the Precambrian, the lunar retreat rate might have been somewhere around 2 centimeters a year. But now what we're seeing from some of the laser measurements is that the rate is now about 3.5 or so centimeters a year. So we can see that the moon is moving away faster.
Now, it happens to be large today, larger than the average over the last 2.5 billion years because of the far-flung distribution of continents. When we had a single Pangaea continent, there was not as much interface, not as much friction. It was easier for the bulge to move back and forth when the Earth was mostly open ocean.
As the moon continues its retreat, it'll cause our days to get longer and eventually throw our seasons out of balance, destroying life as we know it. To see what our future might look like without the moon's strong, stabilizing presence, we can turn to our close neighbor for an answer: Mars. For the past 4.5 billion years, our moon has served as a protecting force for Mother Earth. It's created Earth's stable axis, predictable seasons, and ocean tides. But now the moon is retreating at an ever-increasing rate, so those life-giving constants are about to change. Clues as to what we might expect may exist 55 million kilometers away, on Mars.
Mars is kind of neat because we consider it kind of a sister planet. We can see a lot of similar features on Mars that remind us of Earth and a lot of different analogs.
Mars and Earth have many features in common. They both formed around the same time from similar rocky material. Mars' red color is a product of hematite, an iron compound found all over Earth. Like Earth, Mars also has ice caps. In 2004, scientists' knowledge of Mars expands with the landing of rovers Spirit and Opportunity. Close to its landing site, Opportunity finds tiny evidence with big implications. Scientists don't find liquid water, but they do find strong evidence of it in what appear to be riverbeds and concretions. Concretions are small balls of minerals stuck together like concrete. On Earth, concretions form when water leaches slowly through sediment, dissolving minerals that can harden into balls. A team of scientists is searching for earthen concretions to see what they may tell us about Mars' past and perhaps our future.
Okay, Johnny, here is a place where you see some layers, and we'd like to get closer to it, because that's where we expect to find these concretions. So, these layers are formed at a different time in the history of the Earth, and what we find there are concretions which are similar to the ones that have been found on Mars.
The team tests a remote rover designed to one day explore Mars.
So that's what we'd like to sample. If you could close up to there.
Forward again.
Yes. Here this could be a good spot. So we are going to get samples.
This entire expanse of Utah desert was once the bottom of an ancient ocean. If the concretions on Mars were formed in the same way, that means that a large body of water was also present on Mars. If so, then like Earth, life on Mars would have been possible. So could we one day lose our liquid water? This is what Earth's future might look like without liquid water. A barren, lifeless rock. Like Mars, what water might remain would be frozen mostly below Earth's dusty surface.
It is interesting to think that Earth is a very dynamic planet compared to Mars, but Mars in its past history must have also been dynamic. And what's happened? Maybe there is some similarity in what our future might be.
Mars' axis is 25 degrees, just 1.5 degrees more than Earth's. Mars also wobbles periodically on its axis, but Mars' wobbles are far more drastic. Nearly 100,000 years ago, when Earth wobbled less than 2 degrees, it caused an ice age. Mars wobbles up to 60 degrees, producing a severe climate and creating an uninhabitable planet. That's because neither of Mars' moons are large enough to stabilize it like Earth's moon does. Mars' moons were not made from their mother planet, but captured by Mars' gravity as they passed by. So their gravitational effect on Mars is far weaker than our moon's effect on Earth.
The Earth-Moon system is stable because it's locked in this rotation, and the Moon is stabilizing that. And if you just have a sphere that's rotating, it's basically free to rotate in any direction it wants. And that can happen to planets that don't have a moon to stabilize them, like Mars would have a kind of a more random walk of its axis.
Our moon's gravity works a bit like a brace, preventing the Earth from toppling over. Planetary scientist Dr. Jack Wisdom uses a simple gyroscope to illustrate. This gyroscope is like a spinning top, only it's mounted inside a frame or gimbal whose axis is free to take any orientation. When set in motion, it behaves like a rotating planet.
This is the regular precession. If we just hold the gyroscope fixed without swaying the string, it's analogous to the Earth.
Besides gravity from the Sun and Moon, the largest planet, Jupiter, also pulls on Earth. But our moon greatly reduces the forces of Jupiter. Mars is not so lucky. Without the stabilizing influence of a large moon, Mars is more vulnerable to the forces of Jupiter and larger planets.
And now I'll force it.
Dr. Wisdom simulates those forces on Mars' angle of rotation or obliquity using a string.
If we begin to force the gyroscope by swaying the string, then the gyroscope will undergo very large variations in obliquity. That's analogous to Mars.
So, the current, even 25-degree tilt of Mars' axis is only temporary. Its tilt actually varies over millions of years. Those large variations cause Mars' North Pole to roll over, point at the Sun, and then roll back again.
And so Mars has an axis that's chaotically tilting. Its rotation axis is chaotically changing wildly from 0 to 60 degrees and back and forth, and it's tipping over on its side on geologic timescales. It's actually quite frequent. So if the Earth didn't have the stabilizing moon, would we be more like Mars?
Without the shield of a moon's gravity, Earth becomes vulnerable to other, more powerful forces in the universe. Jupiter, the largest planet in the solar system, begins to take over. It's separated from Earth only by smaller planet Mars. And because it's 11 times wider and over 300 times heavier than Earth, its gravity overwhelms Earth. So when Jupiter lines up just right with the other planets beyond it, their combined gravity over millennia begins to pull Earth over.
So you can see what would happen if we changed the tilt of the Earth's axis, would change the angle of the sun's rays coming in relative to the Earth. And this would wreak havoc with the climate that's on the Earth right now.
This drastic tilt changes the angle of the sun's rays on Earth, melting ice at the poles. And redistributing the ocean bulge away from the equator. But unlike Mars, Earth would probably retain much of its liquid water due to its magnetic field. So Earth's oceans could rise tens of meters, wreaking havoc around the world. With our moon's retreat from Earth increasing, it's possible that this may be a glimpse into Earth's future. Without the moon's protection, the Earth would be more vulnerable to gravitational pull from larger planets like Jupiter. Earth's even 23.5-degree tilt, or obliquity, would be a thing of the past, and our planet would begin to topple over. Initially, this causes massive coastal flooding. And over millennia, things go from bad to worse. One astronomer in Paris has figured out just how bad it could get.
Without the moon, I would say that the natural behavior of the Earth would be to have an axis that would oscillate completely widely.
Dr. Laskar's 1.5 billion year time-lapse demonstrates that when our moon is removed from the picture, the Earth's axial rotation becomes chaotic. Total chaos also means that scientists cannot predict exactly which way or how far Earth will tip over. Dr. Jack Wisdom of MIT designed a gadget to show just how unpredictable chaotic behavior is, even in the simplest system.
There are no motors, there are no magnets. This is a double pendulum. That's one pendulum hanging off another pendulum. It's one of the simplest demonstrations of chaotic behavior. I'll demonstrate chaotic behavior just by...
While the single pendulum of a clock provides an even, predictable arc, adding one more pendulum creates complete unpredictability. Like future Earth, scientists cannot predict which way this device falls. Its behavior changes each time they test it.
So if I try this initial condition, I get this rapid spinning motion. Chaotic behavior is behavior that is so sensitive that very tiny changes in initial conditions yield very quickly impossibility of prediction of the subsequent motion.
Despite the unpredictability of how Earth will behave when the moon is too far, the days of chaos are indeed coming. With the moon just 440,000 kilometers away, only 10% further from where it resides now, a chaotic Earth will wipe out nearly every living thing. By 1.5 billion years, the moon will be far enough that Jupiter's gravitational pull on Earth will take over from the moon. In a worst-case scenario, Earth tips 90 degrees, so a pole points directly toward the sun. Both ice caps melt and reform completely every 6 months.
Now you've got the poles that are directly in the line of the sunlight with a very high incidence angle, and so you'll get warmer temperatures there, and you'll have the equator in the exact opposite situation.
That would mean that you could have, say, glaciation on one half of the sphere of the globe and deserts on the other half.
Take away the moon, and water would move away from the equator. An area like Florida could become more arid, wiping out most of the state's agriculture. More direct sun could turn Paris into a desert, covering everything beneath tons of decimated Earth. In North America, severe tropical storms could wipe out East Coast cities, killing millions. In the southern hemisphere, Brazil's Rio de Janeiro could be plunged into 6 months of darkness. Starved of sunlight, it would experience a winter like none the planet has ever seen. Plants would starve, and animals would die en masse.
And that would mean that you would probably have a breakdown of the ecosystem that supports all advanced life.
After 6 months, as Earth moves along its orbit, climates would reverse again. A glacier might engulf North America and recede again 6 months later. But this is not the final chapter in the story of the Earth and its moon. Armageddon could be quite different. Long before the moon recedes completely from the Earth's orbit, our planet is likely to meet its fate by the sun. In about 5 billion years, the sun will have burned up all of its hydrogen atoms and will start to expand.
The sun is eventually going to swell up and become large enough to actually engulf the planets, including the Earth.
As the sun expands, it impacts the moon, exploding it into bits of rock. These moon rocks will circle the Earth much as they did before the moon was formed. Many will rain down, creating the greatest meteor shower since the early days of Earth. But this won't be the Earth's final fate, because the sun is likely to continue expanding until it engulfs our planet entirely.
And so then we won't have an Earth-Moon system left to deal with anymore. So the demise of our solar system will be driven by the sun going through its life cycle. It was born, and then it's going to die, and it's going to take all of us with it.
But for nearly 2/3 of the sun's life, our moon will have served as our protector, our stabilizer, our sentry at the gate, ensuring that life as we know it will continue. For now.